still coming up. And when we started doing more and more research, just because of the geography where we are living in, as Shrimali sir said, we are living very close to California. Everything we discuss, any building type, it's always the seismic performance, seismic factors that govern our design, that govern our design decisions in that part of the world. So, and over the years, a lot of things has happened in the destructions that has happened. If you look at Christchurch, 2010 earthquake, even the 2001 earthquake in Gujarat, and later on, previously 94 in Northridge in the US, and so on, and some recent earthquakes in Nepal. There is a lot of discussion in the structural engineering community that can we do as a profession, as engineers, can we do better than what we have done before? So can we make much more better earthquake withstanding structures? And also at the same time, can those structures be functional after the earthquake? So that's what we are trying to do, is performance-based seismic design with functional recovery. There are two different parts of it: performance-based design and then functional recovery. And we will tie the two together probably towards the end of the program, but let's talk one by one between performance-based design. What is performance-based design? And Shrimali sir and Dr. Roy introduced it a little bit. We will delve more into it. So we'll talk about performance-based design, then we'll talk about functional recovery, and then how we bring them together is what we'll learn, probably day 5 of the program. If you have any questions, please ask. As I said, I'm no way an expert in this. I'm also learning as we go along. So once we figure out a path forward, we'll come up with something much more functional. The other thing, please forgive me my jet lag. I am a bit jet lagged, a bit tired, so please give me some latitude. And if I fall asleep during the lecture, please wake me up. So let's talk about, before going to performance-based design, let's talk about code-based design. So what is the seismic code of India? 1893, right? What about other parts of the world? Do you know any of the other codes? EC 8, Eurocode, and in the US, and you base your sizes of the beams and columns based on your demand. So that's our general method, which is the code-based method. So building codes, they specify requirements. Right? So you have your structural demand. You have to meet that with your capacity or factored down capacity, which is your design strengths. Building code gives acceptable, if you do that, you think those are acceptable solutions. Right? But there is no performance check. We'll come to that in a minute. And essentially, building codes are prescriptive. Everybody agree with that statement? Building codes are not prescriptive? They are? Okay. So what do they limit? If I prescribe something that you have to follow like a cookbook, what am I taking out of the equation? Innovation and out-of-the-box thinking. So you're just using your recipe book to follow, and you're getting your strengths getting your structural members based on that. And then there's a lot of other solutions that could be acceptable, which are not being considered or not on the table. And it's also based on experience, right? So if you're just using prescriptive method, Ramana sir might design a whole building in 10 seconds while it'll take you 2 days, just because of his experience. So there is that factor as well. There is an implicit nature of the building code, which is that it implicitly ensures public safety. That's what, it's a policy document, it's a law that you have to follow. But the implicit nature of it is that public safety and convenience is an implicit check rather than an explicit guideline. So as I said, codes are inherently prescriptive. Performance of the structure is ensured implicitly. By that, what I mean is you follow these checks, right? You design for your bending moment, design for shear, then you check for deflection. What else do you do? That's it, essentially. So you do that, and then the building code, and you will assume that the structure is safe. So it's an implicit check. There is no performance check. How would you do a performance check? If you have to do one, how would you do it? We will come back to that in a few minutes. So if the building code is not allowing for a performance check, or you're not able to do it, you don't know whether the building is performing up to your designed capabilities. There is no way to do it. Performance checks you can do is either by very high resolution finite element models, or you can do experimentally with the facilities probably you have downstairs. So there are multiple ways of doing performance check. These are the two ways. But without the performance check, whatever performance happens may or may not be acceptable. Any questions so far? So what are some of the shortcomings of code-based design? So they are generally a policy document, right? And they were written keeping in mind the low-rise building, not the tall buildings in general. Tall buildings have had different behavior mechanism, especially when the ground is shaking during an earthquake. There are like higher mode effects, dynamic amplification that happens. So generally for tall buildings, a different set of guidelines are needed, and the world is moving towards that. Generally, the codes are written for low-rise buildings. It's pretty much prescriptive in nature and limits the structural system that are listed in code. So there's moment frame, there could be a steel BRB, there could be a balloon-type shear wall system, and so on. There are a few different systems that are listed in code, be it IS code, EC, or your IBC, which is the International Building Code, which is in the US. So there are very less structural system that can be used. Again, it's based on elastic method of analysis. Does everybody know what elastic method of analysis is? Yes. Can somebody explain?
The stresses are below the elastic limits. Limited to the elastic.
Stresses are below Hooke's law. So generally, we are trying to maintain that, right? And then detailing are again prescribed. So how much reinforcement, what's the area of steel, how much cover, everything is kind of prescribed in a sense. And it does not take advantages of the recent research. People are doing a lot of good research in every part of the world, and those research can be collated and can take the building code forward for much more optimized design. The code cycle is such that it takes 3, 6, 10 years sometime to come up with a new code, and then those research results are not really incorporated within there. So that leads me to the question, are these building codes correct? What do you think? I know you have been taught like building codes, you have to design to the code, but have you ever questioned, are these building codes correct? There has to be, right? Yes or no? Or maybe? Maybe. So generally there are inherent set of assumptions, and we are, as structural engineers, we take pride in being conservative in our design. So with our conservatism, we are ensuring that we are playing safe. And we are taking a lot of guesswork out of the equation. Building codes are generally okay worldwide, but they are very conservative in nature, right? And if the building codes, if one building code is correct, then how is there difference between 2 or 3 different building codes? How is IES 1893 different from EC8, different from International Building Code? Why are the methods a little bit different? And as Shimali sir said, codes generally are intended for life safety. They do not have any other performance parameters, right? Generally, life safety is the main function of a building code. It does not consider damaged states or functional recovery or cost of repair or cost to rebuild in that sense. How codes ensure safety? They define appropriate hazards and load levels, right? You have load combinations. Those are your load levels. What I mean by define appropriate hazards, you know what they are? Is there a SLE, MCE, kind of different? Do you know what a response spectra is? And are those response spectra different for different return periods for earthquakes? Yes? So those are different hazard levels. So different return period. If it has a higher return period, that means it's a much more massive earthquake than a lower return period. So for a higher return period earthquake, you probably need to consider higher forces. And then in terms of building codes again prescribe limits on structural system and defines the procedure and analysis that you can carry out, specific rules for detailing, and there's a design checklist that you follow, design for moment, shear, check for deflection, and you call it good. And there are specifications also for construction and monitoring of the same. Now let's talk a little bit more about the motivation of seismic design, especially from a US perspective, but I'll try to bring in the other countries and what happened over the world and how it has filtered down and how we ended up with this new paradigm of design. So 1971, a massive earthquake happened in the San Fernando Valley, and you can see the structure there. The structure, you can see how it tilted and the other part collapsed. This was one of the first prominent structural damage that triggered a lot of discussion at different levels, especially in the Western world. The stair tower collapsed from the building, and there was a near collapse in the second story, and there was a lot of other damages in and around that area, which really triggered a lot of discussion as to what we can do better as the next one happens, right? So after this 1971 earthquake, there was a lot of workshops that were conducted to improve the building design codes at that time. 74, Structural Engineering Association of Engineering Association. Essentially, SEOC is a very major association of structural engineers in the US, and they really inform the building codes together. Once they make a change, they would inform it to American Society of Civil Engineers as well as to the International Code Council, which writes the IBC or International Building Code. So they adopted some quick changes. So looking for higher forces, soil factor was introduced, importance factor for building was introduced. The Indian Building Code has something similar in terms of importance factor, I think. And so those were introduced in 1974. There were a lot of ATCs, Applied Technological Council. It's funded through FEMA and the federal government. FEMA is Federal Emergency Management Agency. It's similar to NHD, National Hazard Disaster Management Center, that the Indian government has. And so they funded a lot of projects that did some experiments, triggered some fundamental changes into the way we design. Congress passed the Earthquake Hazard Reduction Act, where it's essentially mandated, the law was passed at the federal level that it would like less damages as well as more life safety. Again, there was an executive order. I know Mr. Trump is signing a lot of executive orders these days, but this was one that was signed by the president at that time and then was kind of executed over the years. And then they established a federal earthquake risk management standard in 2016. So from there on, between then 1990 and 2016, another thing happened, which was not in the US, but in New Zealand. In 2010, Christchurch earthquake happened. And New Zealand has one of the most advanced building codes in the world, especially for seismic design. So if you get a chance, read the New Zealand Building Code. And New Zealand Building Code is nothing like US, Europe, or Indian Building Code. And it is based on performance-based design. It is not based on prescriptive measures. Or it has a provision for performance-based design. But New Zealand government said that we had a lot of damage during the Christchurch earthquake. The buildings were fallen. Buildings survived, but was not functional at all. So New Zealand government then passed a law that now we have to do designing for the building, where not only it has to be safe, but within a matter of weeks, people can come in the building and start working or living again. Earlier, once an earthquake happened, the building would probably be damaged so much that it has to be torn down or bulldozed, or the repairs might take a year or maybe a year and a half. But the New Zealand really took a proactive step and said, no, we want it to be functional within the few weeks of the earthquake. And it's a different matter that a lot of aftershocks happened after the 2010 earthquake, and that really made things complex, but this was one of the drivers for performance-based design and functional recovery coming together. So this was the ATC report that I was talking about. Again, it was first published in 1978, but the new approaches, it said that instead of every state having its own code, we'll adopt a nationwide. So in the US, things are a little different. Every state has their own building code, but they wanted a nationwide policy document. It has to be probabilistic in nature, and that's where the return periods of different earthquakes came in. Then instead of elastic nature, they also wanted to take into inelastic behavior and also talk about strength level. Non-structural elements were talked about in a lot of detail, because when an earthquake happens, generally the structure survives, but it's the non-structural details that really are the one that is rendering the building non-functional. So when I talk about non-structural details, what do you think I mean? What are non-structural stuff in a building? Anybody?
Boards which are not designed.
Which are not designed. Windows, your HVAC system, your plumbing system, your electrical system. So if your building has a capability of 2% drift and they are not designed for 2% drift, then they will crumble, and then your building is not functional. Again, I won't go into a lot of detail here, but after that San Fernando earthquake, we had a lot of different materials of choice: reinforced concrete, steel, lumber, plywood, masonry. They all came up with their own codes and standards for earthquake engineering or earthquake design. And that was what fed into the NEHRP provisions, which is, NEHRP provision is the one step before it gets incorporated into the building code in the US. There are review committees, there are trial designs, there are numerical modeling, and the first edition of the recommendations came out in 1985, and then every few years, a new set of recommendations and guidelines are coming that is fed into the new IBC, or International Building Code. In the US, there's a 3-year cycle for the building code, and then newer and newer guidelines are coming, but everything is still prescriptive, nothing is performance-based. So as earthquake engineers or as structural engineers designing for earthquake, our guidelines are minimize human death and injury, minimize economic loss, and the economic loss could be direct and indirect, and also maintain lifelines. So what does these 3 bullet point means? Minimize human life is pretty simple, right? You have to prioritize life safety. That is a given. And then also you have to look for the economic downtime or economic losses. What are direct losses and what are indirect losses? Direct losses could be the building is collapsed, right? Or the repair that is needed. The monetary value of the repair that is needed to bring the building back to functionality is one of the direct costs. Indirect cost is loss of time. And if there is a business or institution is housed in there, what about the functionality and the losses that institution or the business would take while they are out of a building? Those kind of things. Another aspect not related to building structures, but maintaining lifelines. So infrastructure lifelines are something like your bridges, your pipelines for waterways, and so on. So those needs to be designed so that it is maintained. So these are just worldwide figures of how much losses different hazards took over the years. And you can see the few of the earthquakes, like earthquake and tsunami in Japan in 2011 was one of the highest economic loss event in the world. Kobe earthquake in 1995, Hurricane Katrina, it's a natural hazard but not related to seismic. Northridge earthquake in 1994, which really changed the building codes in the US, especially for timber. Again, was a very high damage earthquake. And just in the US over the years, typically earthquakes are at 25% of the total number of dollars lost in different hazards. Wind is a big one, especially in the US. There's hurricanes, there's tornadoes, there's a lot of damages in that area, so the rest of all is wind. But wind design is much more easier than seismic design, so it generally doesn't get that much attention. But earthquake is, especially because California, it's one of the richest state and one of the states with highest economy, is under the seismic zone. You talk up a lot about California and the seismic zone within the west coast of the United States. Anybody remember this event here? The 2004 earthquake tsunami combined was a massive, massive loss globally. The earthquake in Haiti in 2010, Japan, Nepal in 2015, and the recent one also. So again, there's a lot of damage and deaths associated with earthquakes. over the years. Example of some big earthquakes over the years, especially in the US, and the list is growing as we speak. Worldwide, there are a few to mention. Is 1985, Mexico City was a huge one in terms of lives lost. Japan 2011, Mexico City 2017, Haiti. This was the Gujarat earthquake in 2001, Republic Day. That was a big one, also for India. This was some examples from the Mexico City earthquake damages that occurred. This was one of the few steel frame buildings that collapsed. This was the 2011 Christchurch earthquake. This was a massive one because there was not only buildings that failed, the liquefaction happened, and there were like 10,000 aftershocks that come. So there's a main shock, right? The earthquake comes, main shock. And then over multiple days and weeks, there's small shocks that comes in. Now, with the main shock, your building is already kind of damaged, yielded at some places. And then with the aftershock, it does not take much to collapse the building. And the aftershock did a lot of damage than the main shock in the Christchurch earthquake. So in general, we build, right? Especially in the Western world, this is true. An earthquake happens. And when we build with earthquake, we are not exactly building because we can't predict how will the ground vibrate. It's only guesswork. Then the ground vibrates or the ground shakes. Then damages occur. We note those damages down, we do some analysis, we learn from those damages. That propels or catalyzes a lot of research with a lot of universities. For example, the 1994 Northridge earthquake gave rise to something called Consortium of Universities for Research in Earthquake Engineering. If you have been part of some testing here with the cyclic testing profile, one of the cyclic or cyclic testing one of the cyclic testing protocol that is used predominantly in the world is called the Curie protocol, which is where the amplitude rises with every cycle, or every 3 cycles. And that was a culmination of research from that Northridge earthquake, after the Northridge earthquake, with the Consortium of Universities for Research in Earthquake Engineering, which is Curie. And from that research, you go to code development, and the cycle goes on. Again, a little bit more. This is not a one-person job or a one-field job. It's not just structural engineers. There's a lot other fields that are providing input. There are folks from construction, architecture, education, policymakers. Insurance is a big deal. Like, they dictate a lot of policies in the Western world. Research. The social impacts of the downtime in the building is massive as well. Economics, seismology, hazard risk assessment, geology, and so on. So everybody comes in, and then the built environment thrives. And you talk about, Professor Roy talked about dams. Dams is a major part of infrastructure which needs to be seismically designed. So there's a lot of stakeholders within the designing team. Again, some of the documents which I mentioned. These are the NEHRP recommended seismic provisions for new buildings and other structures. This is published by FEMA, Federal Emergency Management Agency. Now, in the US, there is a saying that if the federal government or equivalent of the central government here publishes something, that's as good as code, even though it is not a building code. These are just guidelines. But if they publish us something that's as good as a code, and that it can be incorporated without a lot of discussion into the building code. So the FEMA publishes this every few years, and FEMA has also other documents that goes into the building code. Then ASCE 7, which gives the minimum design load for buildings and other structures. So IBC, International Building Code, refers to this document for your load combinations, your wind load maps, your seismic hazard levels, and so on. And then there are design manuals for concrete and steel for, again, IBC says for concrete design use this, for steel design use this, for timber design use another code, which is the National Design Specification for Timber Construction, which is a timber code. So it's a convoluted process. Generally, I like to say structural engineering is the art of using materials that have properties which can only be estimated. You don't know what the exact properties are. To build real structures that can only be approximately analyzed. Like even if you're building a very high resolution numerical model, again, the model is an approximate solution, it's not a complete solution. To withstand forces that are not accurately known, right? We are just guessing what would be the hazard level, what would be our forces that are coming into. Therefore, we need to design structures to satisfy public safety. So to summarize, generally, the majority of the construction in general in the United States and worldwide consists of low-rise building, right? 1 to 3 stories is 93% of the building globally. 4 to 13 stories is 6%, 14 stories and taller is 1%. The code generally says it's applicable to all these 3 building types. But we know from research, a 14-story building behaves much more differently under high-speed wind event, like a tornado or a hurricane or an earthquake, than when you compare it to 4 to 13 stories or 1 to 3 stories. There are higher mode effects, there are higher dynamic amplification as you go along. So the one-size-fits-all approach might not work for all these 3 building topologies. Prescriptive methods are not written for taller buildings in general because they are generally catering to 1 to 3 story structures. And in some cases, some countries, 1 to 4 story structures. And for 1 to 4 story structures, generally it works just fine. And I wouldn't even recommend any other design method for 1 to 3 story structures because it's just not cost effective. But for taller buildings, I think we need a much more different design philosophy than what the code provides. And prescriptive codes are not equipped with means to distinguish differences that are tied to the response of taller buildings, as I said, higher mode effects and dynamic shear amplification, which are 2 very known phenomena for taller buildings. So just to summarize, in a code, what do we do with force-based design? We estimate a probable lateral seismic force, which is base shear. Everybody heard about base shear? Shear at the base of the structure. And then what do we do with the base shear once we calculate it? Can we louder, please? Distribute the base shear along the height of the building at the story levels, right? Then we design, the design is carried out with prescribed load combinations. And we use a graph which is called the response spectra. And generally all the response spectra are designed or provided with 5% damping inherent to it. If it's more than or less than 5% damping, you have to create a new design spectra. Or you can calculate equivalent viscous damping. The design response spectrum is a smoothened average of large number of earthquakes in the past, because we have the ground data for them, and probable future simulations of earthquake, because we don't know how the ground will shake in the next earthquake. So those are probabilistic simulations of the future earthquakes in that region with the history that we have in our knowledge bank of that region and how it'll behave. Any questions so far? This looks familiar? Can anybody tell me what the x-axis is? Period. What's the y-axis? Spectral acceleration in terms of g. And what are these plateaus and response of a single degree of freedom system? Okay. So I'll probably not spend more time here because it looks like everybody knows, but this is important. And in performance-based design, we use this to generate what we call displacement spectra. We'll talk about that when we do performance-based design. So in terms of different building codes, there is something called seismic response modification factor. What is it? So if your building is totally elastic, what will happen? What does this line will look like? Straight line, right? And if you design for a building that is totally elastic, what are the consequences? Is it optimized design? Can you be louder, please? Heavier sections, larger sections, very costly, right? So what we assume is something called equal displacement. And in earthquake, it's not a mathematical principle, but it is an assumption that a building will have equal displacement in an earthquake equivalent to what it'll have if it's totally elastic. So your actual behavior is assumed to be something like this, and then this is your delta U, or delta ultimate. So instead of designing for this force and this displacement, you're designing for this force and this displacement. And this difference is what is called your seismic response modification factor. And why is this factor needed? Otherwise, you'll be designing a very large cross-section for beams and columns and a very heavy, costly building, where you're ensuring safety, but then you're not ensuring cost effectiveness. Any questions so far? When I mentioned in the PowerPoint that different building codes have different ways to calculate things, for example, in the US building code, you have something called V equals CS over W, or times W, and CS is further given by SDS So R is the seismic response modification factor, and that is dependent on the system itself. For example, a moment brace frame would have a seismic response modification factor that's already listed in the code. A light frame shear wall for, light frame wood shear wall for, as per the IBC, has a seismic response modification factor of 6. At the moment, brace frame, I think, is a 7.5. The highest is about 8. SDS is your short duration displacement and design-based spectral acceleration. IE is the importance factor. Again, different building types. If it's a house, it's a hospital, it's a school, have importance factor associated to it. Which one would be higher? School or a residence? Or a hospital or a residence? Hospital, because it's a much more important building type. Needs to be functional during an earthquake for people to come and gather as well as get medication. This is your weight, your seismic weight. Any questions so far? How is it different from what's in the Indian code? This looks familiar? What's Z or Z? Zone factor. How is it defined in the Indian code? Okay. I is importance factor, again given in the code. R is same, pretty much the same thing. SA over G. Spectral acceleration. W, the building. So essentially, you'll see there are subtle differences, but not much. Eurocode is also the same way, where you have a different, for base shear, you have a different terminology. So in Eurocode, essentially, they will get an FP, which is base shear SD times T1 M over lambda. Or SD times T1 or SDT1 is from the design spectrum. M is the mass of the building. Lambda is a correction factor for which is either 0.85 or 1, depending on where it is. So in general, they don't have the importance factor and the seismic response reduction factor, but their design spectra is a little bit differently constructed than other places. Any questions so far? So in summary, you're just calculating base shear, right? Which is a force. But during an earthquake, what do you want from a building? Structural component should not fail, okay? So that's a strength requirement. Then, okay, my structural component does not fail, but my building deflects a lot. So there should be a stiffness-based requirement as well, right? It should be stiff enough to not undergo that much deflection. And then the earthquake is putting in a lot of energy in the building. How can I dissipate that energy? That's a ductility requirement. So I need to design my members or design my rebar in such a way that those are ductile, which we call ductile detailing, right? Or we can have other kind of dampening system and base isolation and those kind of things. That will increase the cost of the building. But given that maybe it's not a high-end building, we have stiffness, strength, and ductility requirements, right? Now, all these requirements have something in common, which is they may be looking like force-based requirements, but they are also deflection-based requirements, and we'll prove that in a minute, right? So in a building, it should maintain sufficient stiffness to dissipate, sufficient stiffness so that displacements are kept to a minimum, right? A stiffer building will have less deflection for the same force, right? So stiffer building and maybe a less stiff building will have, for the same force, let's say if we pick a point here, for the same force, the stiffer building will have less deflection. The stiffer building will ensure that your non-structural elements are not damaged that much, because the building's not going to drift that much, so your non-structural elements are protected, which is a consideration. Then the strength-based requirement, which is in a medium-sized earthquake, we want to ensure that there are no structural damages, and the stresses that are imposed by displacements remain in the elastic region for moderately severe earthquake. So if they are in the elastic region, that means your building is stable. So in which part of your force displacement functionality would that be? Would it be in this region, or would it be somewhere here? In the linear region. And the building should be, for your ductility requirement, the building should be ductile enough to withstand displacement demands for a very large earthquake. So if you think about it, if you think through the words, there's displacement here in the stiffness requirement, there's displacement here in the strength requirement, there's displacement here in the ductility requirement. But yet we are designing for forces. So another parameter that we could probably use in design is displacement. And that was the genesis of displacement-based design, which is one of the types of performance-based design, where you design the building to achieve 2% drift or 1.8% drift at the maximum considered earthquake level, something like that. So at one of the hazard level. Any questions? So coming back, and I'll try to bring it all together. To deal with high earthquake forces, if you want to be at the elastic level, you have to pay the premium in terms of costs and much more non-optimized design, or you have to increase damping from other outside methods, which are all costly. Or you can allow controlled inelastic response, right? That's what we try to do here, is controlled inelastic response. Any questions? Okay, so should we take a 5 minutes break and we'll switch over to our next topic, which is based on the displacement. Let's talk about how displacement-based design and performance-based design really came into picture. So let's take a 5-minute break and then we'll start that. So if you can be back here by 12:20 or 12:22, we can start that.
You can just go washroom and come, don't go downside.
Yeah. Don't go for a tea. How's it going, sir?